just to give you a bit of background, Josh Chang is a product manager at PixArt Imaging. He's been responsible for gesture products since 2014. Currently responsible for planning and marketing PixArt's latest ultra-low CMOS sensors, image processing, and reality vision-based detection at the low wattage. Josh has a background in electrical engineering, got from National Tsinghua University, and has been in the industry for the past 20 years with a lot of system-on-chip design, embedded flash, and IC design with Realtek, Macronix, respectively. So, Josh, thank you once again for your time, and please go ahead with your presentation.
Okay, thank you, Nicholas. Good morning, everyone. My name is Josh Chang from PixArt, and it is my pleasure to be invited to the tinyML Asia. Today, I would like to share about sensor fusioning of FIR thermal sensor and the image sensor through the machine learning to enable the smart forehead temperature detection applications. My main coverage today will elaborate on the background of forehead temperature sensing devices in nowadays and the target product we want to achieve. I will describe the block diagram of PixArt solution and explain how it works. Then I will share some challenges and how we overcame to explain the tinyML's benefits on the application. PixArt is an IC design company focused on developing image analytic type of sensors. CMOS image sensor is our core competence. However, we put a lot of focus on incorporating algorithms into our sensors. With the hardware algorithm built-in sensors, the system can reduce a lot of computing power. PixArt is dedicated to provide ultra-low power sensors for image analytics. With the increasing demand of battery-driven devices and always-on detection applications, the low-power sensors and the low-power processing plays a critical role in making this reality. There have already been many discussions around this topic. However, to take this discussion further, if the sensor itself can provide a first-stage data analytic before waking up the host, that could not only reduce the number of false detections that utilize unnecessary system power, but also extends the power usage duration of the system. PixArt's approach is to provide such kind of sensors that would be helpful for the always-on detect applications. On the sensor front, we try to think if the sensor's data can be preprocessed, or can the processed data from one sensor be able to complement another sensor? How can such sensors help to enhance better user experience? In the following slides, I will show PixArt solutions with sensor fusion that uses our FIR sensor along with our ultra-low power CMOS image sensor through the low-power machine learning processing chip. The purpose of this processing chip is to realize a proof of concept for low-power application with our sensors, and to further explore future possible usage with our sensors. This could be a good example of how the draft from each sensors can help complement each other through the machine learning process. Let me use the demo video to describe this application first. Nowadays, the most common way to monitor body temperature is using the handheld forehead thermometers. This device is small and the accuracy is very good. However, the sensing distance is very close, need to be within 5 centimeters. If using this in the public area, it will need another person to hold the device. This face-to-face measurement will increase the risk of infection, and the social distance between these two persons will be difficult to keep over 1.5 meters. Another device we often see in many public areas is the high-resolution thermal image solution using barometer. My colleague in the video is holding a cup of hot coffee. As you can see, the temperature result is unstable or disappear. It is affected by other heat sources, which is higher than body temperature. The sensing distance of this solution is far, and the temperature accuracy is also good. However, the barometer's price is very expensive, range from a few hundred US$ up to few thousand US$ for the whole system. The device size is bulky, and usually need to be bundled with PC, which makes the system architecture very complex. Let's see what PixArt solution could help to address the need. When a person comes in, the device automatically measures the forehead temperature and identify if the face is wearing the mask or not. Now is the case without mask. You can see the temperature result output response is fast. Then how about holding a hot coffee? As you can see, the result is not affected. And this will show the As shown in the video, the temperature measurement for a visiting guest at the entrance of the building becomes easier. The video shows the solution with affordable cost, similar in accuracy to high-end pricey barometer, but offering longer sensing distance up to 1 meter with adequate accuracy. Our solution is in small, compact size, allowing it to be easily integrated into embedded systems and can be set up anywhere. To enable support for the battery-driven or handheld device, it has to be low power too. On top of these, we wish to provide more smart functions such as detecting face with mask or not, ruling out any undesired heat sources. These smart functions differentiate our solution from the current solution on the market, which can only measure temperature passively. Let's start from the hardware blocks to see how it works. As you can see, we integrated all the components in a compact size PCBA, only 4.5 centimeter in length and 2.3 centimeter in width. With this compact size, it is easy to be installed in many places. The blue label part in A, B, and C are the key components developed by PixArt. More detailed functions of these components will be described in the next slides. Let's see the interconnection of the hardware blocks first. The QVGA image sensor provides the image data through DVP interface, and the 8x8 FIR sensor provides the 64 pixels thermal raw data through I2C. The output data of these two sensors are all fed into the machine learning image processing chip. The processing chip will do face detection and the face mask detection, as well as calculating the compensated temperature. The offline pre-trained model file is stored in the SPI flash. When there is a face detected, an interrupt will be triggered by the processing chip to inform the host to read out the data through I2C or SPI interface. Let's have a quick overview on the key components. The component A, PAF9701, is the 8x8 far-field infrared thermal array sensor module. It mainly detects far infrared heat radiation with a wavelength in the range of 5 to 15 micrometer and converts energy into temperature through the algorithm inside the sensor. It can measure the temperature without touching object, which is suitable for a wide range of applications in daily temperature sensing. This sensor can not only detect the heat radiation source, but also can customize the temperature compensation according to various application requirements to improve the accuracy. Besides, the power consumption is very low. It only consumes 5 milliwatts when full operated and under 10 microwatt in suspend mode. The component B, PAG7920, is an ultra-low power QVGA global shutter sensor module. We prefer to use global shutter sensor in this solution because the sensor can run at slower frame rate for low power applications. In view of algorithm computation, we do not want to see an image with rolling shutter artifact while running in the low frame rate. The sensor itself has built-in auto exposure and the auto gain control function, which means the sensor can self-adjust the setting according to the environment changes. No additional computing power to be spent on the back-end chip. The most special part is that this sensor has built-in a very low power motion detection mode. The power consumption of this mode consumes less than 100 microwatt. With this mode, the sensor can do the first stage motion detection without waking up the whole system, which is very usable in always-on detection application. Lastly, with PixArt's unique power-saving architecture, the sensor outputs the monochrome image with very low power. It only consumes less than 800 microwatt at 15 frames per second operation. Although the sensor has ultra-low power consumption under low frame rate, the maximum frame rate of this sensor can support up to 180 frames per second, which makes it very suitable for low power computer vision applications. The component C PAG7681 is the low power intelligent object detection chip. We developed this chip for our sensors to support low power application and also for sensor fusion applications. In this chip, we hardwired a lightweight CNN engine. The model size is only 1.8 megabyte. The net architecture is fixed. However, by changing the pre-trained feature file in the SPI flash, the target detect object can be changed. The report rate of human face detection can support up to 15 Hz. This chip also has color ISP function for color image input and can fine-tune the image quality for detection. In case of image data is required, a built-in JPEG encoder can output the compressed image, which saves a lot of bandwidth. With the hardwired lightweight CNN engine, the chip can provide very low power consumption level. Taking human presence detection as an example, the power consumption is down to under 1 milliwatt per frame per second. And for human tracking function, in 60 milliwatt per frame per second level. The data process flow is that both the sensors capture data simultaneously. Then the processing chip will do face detection based on the CMOS sensor image. In the meanwhile, the face with or without mask is also identified. After the face information is obtained, the thermal data in the face area is located, and the forehead pixels are being allocated. Based on the face information and the allocated pixels information, we can calculate and compensate forehead temperature. The following slides will explain why we need to compensate the temperature with face info to overcome the challenges we faced. The first challenge we faced is that the 8x8 resolution is insufficient to measure forehead temperature accurately up to 1 meter distance. assuming that if the forehead area need larger than 2 by 2 pixels to cover, it will need at least 30 by 30 thermal array to get enough resolution at 1 meter distance. A 30 by 30 thermal array chip cost is definitely much higher comparing to 8 by 8 thermal array chip cost. Thanks to the face position information, we can accurately locate the forehead pixels and calibrate the temperature calculation with correct thermal pixel information. In addition, if there exists a heat source, the face position will have to focus on the analysis for forehead area and rule out the unwanted thermal information. I will show you the comparison of the non-compensated result and the result compensated face information. The data show the forehead temperature measurement result of various persons. Each blue dot and red dot are the result measured from forehead thermometer in repeated times to obtain the maximum value in blue, and the red dot is the minimum value. The target temperature output has to be close to the forehead thermometer. As you can see, in short distance, like 30 centimeter, the result within the range of upper and the lower bound, even if it is not compensated. But when the distance is getting further to like 75 centimeter or at 1 meter, the insufficient resolution effect becomes more significant. The non-compensated result is totally out of the range of forehead thermometer. As you can see on the left-hand side, which means the accuracy is totally not acceptable. However, with face information's compensation, the result will be located within the upper bound and the lower bound to bring the accuracy closer to the forehead thermometer when the measurement distance is up to 1 meter. The second challenge we face is the heat influence. The thermal sensor is very sensitive to nearby heat sources. If we want to keep the PCBA in a compact size, all the components need to be placed closely to each other. In such a small space, the heat induced by the components will dissipate through PCB or air into the thermal sensor, which influences the accuracy of the thermal sensor. As you can see on the chart, if the heated device is placed nearby to the thermal sensor, a 40 degrees C heat source will induce about double the error than a 30 degrees C heat source. Of course, we can add a big heat sink or a fan to lower down the heat, but it will increase the cost and enlarge the system size. To overcome the heat influence, the key is to keep the component's power as low as possible. Please see the thermal image we took to measure the temperature on the PCBA. On the left is the ARM9 core MCU board running at 200 megahertz. It is not yet running any algorithm on it. And the PixArt EV board under full run operation is on the right. The MCU board is at around 40 degrees C, while PixArt evaluation board is only around 29 degrees C. PixArt's ultra-low power image sensor and the low power machine learning chip brings the huge advantage to counter on this issue. When the sensor is dissipated heat in less than 30 degrees C, no additional heatsink or fan is required on system design, and the temperature accuracy remains very good.
Josh, just quickly, we've probably got another 5 minutes. That would be great. Thank you.
Okay. From the previous slide, we can see that tinyML architecture brings the benefits of making the two sensors co-work very well. The first one is that with the image data transfer to face information, it helps to upgrade the insufficient of 8 by 8 thermal resolution to achieve 1 meter sensing range. Also, the phase information helps to rule out the undesired heat object, which helps to keep the thermal calculation accurate. Secondly, thanks to the ultra-low power sensors and the low power machine learning processing, the components are allowed to be integrated closely in a complex size PCBA without additional heatsink and fan. Lastly, the image data and thermal raw data transferred to the forehead temperature, phase information, mask information data not only reduce the data amount, but also transform the data to be more useful apply data according to the application needs. In addition, with the change of the training model, the same hardware configuration may extend to different target applications. Pixar believes that this solution has the advantage of high cost versus performance ratio, fast and easy to control, while maintaining high accuracy data output. It is suitable for integrating into any access control system like smart home doorbell. It can also be set up in any entrance for measuring and monitoring human forehead temperature automatically. Thanks to the small form factor and the low power consumption, we think the next generation handheld forehead thermometer could be made smart by implementing this solution. Besides forehead temperature, since the target object detection can be changed by altering the pre-trained model, more applications could be enabled, such as animal temperature monitoring, people counting, live body detection, or abnormal temperature monitoring in industrial automation. Temperature sensing in the kitchen are also the potential applications. Let's have a quick summary. Through sensor fusion, Pixar provides a solution that is cost-effective, fast, and simple to operate, and with high accuracy. Data analytic built into the sensor helps to reduce system power. Some first stage detection can be done in the sensor to avoid waking up the host processor too often. And incorporating algorithm in the sensors can reduce the data amount and save the computing power of the host processor. With the small form factor and the low power consumption, we believe more application will be enabled. That's all for my sharing today. Thank you. If you are interested in Pixar solution, please contact me or visit our website. Hello, Nicholas. You are muted.
Yeah, I am muted. Thank you, Josh. We probably that's probably a sense that we should have as well that reminds people that they're muted when they start speaking. But no, thank you so much. That was a really great presentation and very topical, especially with COVID at the moment and people wanting to know temperature. I actually see this application as well in industry, right? Especially in assets, looking when things are reaching certain temperatures, your sensors, your PixArt sensors would be quite useful there. But we have a few questions and hopefully I'll start asking them. So one of them is sensor cost and how do we get dev kits if that's possible?
Sensor cost.
Josh, for you. Yeah,
Yeah.
if you can have sensor, if there's any costs and if there's any dev kits for that one.
Yes. Cost of the sensor.
The sensor, yeah. And that's for the 8x8 sensor, by the way, the 8x8 thermal sensor. And look, if you don't have that now, that's fine. We can put that in, when people, we can put that in the WeChat if needed. And for the 7681, what kind of algorithms and networks can it run on?
Sorry, Nicholas, for your first question about
Yes.
the cost of
Yes.
the development kit,
Yes.
I think please feel free to contact us.
Okay.
We definitely have the development kit ready to offer, and I think we can provide the cost of a development kit. But of course, this development kit is not for mass production, so it is a price of the evaluation kit price.
Yep, great. Yeah. Thank you.
And for your second question.
There's 7681. Yeah.
Okay. Please repeat your second question.
Yeah. So for the 7681, what kind of algorithms, networks it can run on? Like what's required? Yeah.
Actually, I think the chip is not like the AI chip or AI processor on the market. Actually, we have, as I said, we hardwire a CNN engine, and it is like more like we shrink based on the mobile net, this kind of architecture. Yeah, and we shrink it proprietary.
Okay, so it's a predefined mission. Yeah. Okay, great. So no problem.
So next architecture is fixed. This chip we just want to prove concept that the low power machine learning process. So we don't want to run a very powerful net on our chip.
Yeah, fair enough. That's fair. A few, I'll just maybe one or two. Does the thermal sensor require calibration?
The thermal sensor itself, we calibrate in-house before we ship out the thermal sensor module. As I said, the thermal sensor can apply to various applications because for the forehead temperature, the temperature range is narrow, something like 30 something degree to 40 something degree, but the accuracy requirement is very need to be very accurate to 0 point something accuracy. But for some application like industrial, the temperature range is wide. So in-house, we need to, based on different application, to calibrate the temperature sensor for different application. And this is a thermal sensor itself. And for the thermal sensor and the image sensor, when they combine together, we still need some calibration on the system side. For example, the assembly error, and because we need to map the thermal data onto the image sensor. So the assemble error will need to be calibrated on the system side. And we can provide this kind of method when designing on the system side. We have some guidelines for that.
Okay, great. Thank you, Josh. Look, really, once again, a great presentation. If you don't mind, there's a few more questions in the Q&A. If you can type and answer those, that would be wonderful. But thank you once again for your time. It was a really interesting presentation. Thank you to our strategic partners who supported us, especially some of the key partners here. We've got ARM, who help with hardware and software. The what's called Edge Impulse for developers on the libraries. Qualcomm Advanced AI Research as well for their support in edge computing. Cynthia around hardware and ML training pipelines. So definitely thank you as well. Platinum sponsors Reality AI for advanced sensing with product and tinyML. Renesas for microcontrollers and microcomputers. Our gold sponsors, Sladen.ai, Adaptive AI for the Intelligent Edge. Maxim Integrated, enabling edge intelligent devices. Seed Hardware, who also had present today. I'll quickly go back to them. Thank you once again for all your support. CMOS, build smart IoT sensor devices for data. SynthSets, and our silver sponsors. So thank you once again. It's been a great few days. Look forward to 2022, as mentioned before, and hopefully see you at some of the future tinyML events. Thank you.